emission issues were not on top of any agenda 100 years ago. And that's why this old invention of Flettner rotor never took a lot of attention or success at the time. However, today, regulations, public opinion, economical factors, and of course, the well-being of our Mother Earth is the most important factor why we believe this technology will become much more common and utilized. So we are a company established in 2012 with the only purpose being developing a modernized mechanical sail. That's the odd-looking cylinders on the photo, which is on the bottom of this slide, with the ship's sea cargo name on it. The other big photos, as you recognize, are the traditional, old-fashioned, as we would say, sails, which have been used for thousands of years in one form or another. However, we have now developed and modernized a 100-year-old Flettner rotor concept, which we call Rotor Sail. Wind propulsion has been around, as mentioned, for thousands of years, but modern shipping has not utilized sails when diesel engines and propulsion technology has developed together with all other types of technologies. There was seen no need for wind propulsion type of solutions. Fuel has been very cheap. Emission issues were not on top of any agenda 100 years ago. And that's why this old invention of Flettner rotor never took a lot of attention or success at the time. However, today, regulations, public opinion, economical factors, and of course, the well-being of our Mother Earth is the most important factor why we believe this technology will become much more common and utilized. So auxiliary wind propulsion, the idea is to support the ship's main propulsion, which still typically is diesel engine powered or electrical motor powered propulsion system, and reduce the propeller power requirement by providing additional thrust force from wind with this rotor sail unit. And I'll explain a little bit later how that happens, because we understand it's not very intuitive how a spinning cylinder creates a thrust force. Anyhow, this we call a hybrid system because it works together with the ship's main propulsion system and provides additional power to push the ship forward. Obviously, this technology needs to be economical, and for any investments, there is a payback requirement typically with our customers. A typical payback period with ships sailing the oceans is a rather large range still today, 3 to 9 years, which depends a lot on where the ship's route is or where the ships are sailing. Are the wind conditions favorable? Is the ship very actively sailing, or does it also spend a lot of time in port? Because this kind of technology only saves fuel and fuel cost when the ship is sailing. This is a technology suitable to many types of ships. The main requirement is that there is some space on deck for installing the rotor sail. And naturally, it also needs some electrical power from the ship's power plant to spin the rotor. This slide describes the Magnus effect, which is the physics phenomena making the thrust force for the rotor sail. So this is actually what makes the rotor sail a useful equipment on board. The Magnus effect happens actually in everyday life as well. We just don't know that it was called such. For example, in any ball game where you have a spin on the ball that's traveling through air, you notice that with a spin, the ball does not travel a straight path anymore. There is a curve. And why does that curved path happen? On the top picture with the football, we imagine that the ball is traveling upwards, so meeting a wind flow against it. And when the ball is spinning counterclockwise on the left side of the ball, the surface flow is accelerated because the ball surface is accelerating the air on the surface, and the air pressure is dropping, so there is under pressure on that side. On the other side of the ball, where the surface of the ball is rotating against wind's direction, wind speed, it's slowing down the flow, meaning there is increased pressure. So there's a lift force created, which is always 90 degrees from the wind flow. And that's the basis for us. We can imagine a stretched ball surface being the cylinder that is spinning on the ship's deck. And when wind meets that spinning cylinder, there is a lift force created at 90 degrees angle, which means also that the most beneficial wind directions are from the beam, from the side of the ship, which is also natural with any kind of sailing vessel. There is no sailing directly into headwind, so it always needs to be some direction towards the beam. I mentioned this is an old invention brought to reality and life by engineers Flettner in Germany, and separately actually a Finnish Sigurd Savonius, who developed the same concept without actually cooperating or knowing of each other. But this was a long time ago, and the technology never took much attention at the time. So then we can anyhow try to think what's happened in between 1926, which is the left side picture, Anton Flettner's first large-scale installation of the Flettner rotor to prove the concept. That ship was visiting Stockholm then. And on the right side, one of our reference ships, one of the installations on a tanker, the Maersk Pelikan, which was installed in 2018. They look somewhat alike, but there's a lot of differences, and how those differences are coming about, we can go through here. So obviously material technology has developed a lot, which allows lightweight materials which are more durable than the earlier solutions, and providing also energy efficiency with the lower weight to be spinning. These design tools for the engineers are much more efficient and accurate, allowing optimization of designs by running simulations, improving the reliability, and also improving efficiency of the processes and speed of development. Digitalization, of course, the buzzword for many things, but for us and this solution, it means automatic operation, again, efficiency by optimizing the use without human intervention. So there is no so-called human error or slow response to changing weather conditions. So automatic response to wind speed, wind direction, ship direction, and so on, which makes the savings maximized. And very important for the crew, it's easy to use. Some people, of course, enjoy sailing as a hobby, but the crew, they'd rather focus on other things than following where does the wind blow right now and how to adjust the rotor sail. Our automation and control system takes care of that. Connectivity is, of course, very different from 100 years ago, and today's remote monitoring and operations support makes it also possible for maintaining very high availability. In case any issues arise, our engineers from our offices can easily contact the crew and agree of any actions necessary, or even operate the systems if so agreed. And of course, all of the above and many other details result in maximizing and optimizing fuel saving and emission reductions, which lead to eventually the required profitable investment to make this kind of technology popular and a growing business. Here's a most technical slide of this presentation. Sorry if it's looking a little bit too dense here, but this is also describing how the rotor sail can produce the thrust force from different wind speed and wind direction conditions. So the figure on the right side with the colors is called the polar diagram, and that describes how different wind directions and speeds, the color codes are from 1 meters per second wind speed to 25 meters per second wind speed, how they create thrust force then with the rotor sail spinning. So we see that the headwinds, they are not giving a benefit. Actually, there is additional air resistance. The beam winds are creating the best thrust force forward for the ship, and the direct aft winds neither are the optimal ones. We remember the 90-degree difference from Magnus effect, the lift force, compared to wind direction. And with these drawings on the left, we see that how the green arrow apparent wind angle coming from different direction leads to the red arrow lift force pushing the ship in certain directions. So we can see that the optimal is from the beam, and then also different angles, they give sufficient forward thrust to justify spinning the rotor sail and using some electrical energy. And that's the job of the control system. This is the algorithm setup that is continuously happening on board. Some words about our reference projects and experience so far. Currently, there are 5 ships sailing in different regions of the oceans and world, which have Norsepower's rotor sails installed on them. 4 different models, and actually today, more than 150,000 hours of operating experience. First installation was in 2014, and this ship, Sea Cargo's SC Connector, a Ro-Ro ship, was installed in late 2020. So although we have already more than 7 years of experience in operation, we are continuously developing our products, and this is the first tilting model rotor sail. You can see the photo on the right side, ship is passing under a bridge, which means that the air draft, the maximum height of the ship is restricted. And on the left side, you see that the rotor sails increase the maximum height significantly. So we needed to develop the tilting model to allow operation on such routes. These units are the largest models, 35 meters in height and 5 meters in diameter. One of the most important facts and statements that we receive from customers is the user experience and how they view operation and performance of our rotor sails. So these are some statements from customers. For example, during their testing, they have recorded an equivalent of 7 megawatts, so 7,000 kilowatts of propeller shaft power coming from the rotor sail thrust force. And with the 3 megawatts of propeller power, the ship could achieve a speed of close to 20 knots. With only the main propeller power, ship can achieve roughly 16 knots. Our most recent delivery is on a huge ore carrier, the LOC, very large ore carrier, which is sailing between Brazil and China, transporting iron ore from the Brazilian mines to China for further processing. And these ships are sailing for several weeks on their long voyage, and the wind conditions are generally quite favorable for fuel saving. So these 5 medium-sized rotor sails, which are also tilting model, as you see on the right side, are estimated to save about 8% of the ship's fuel consumption, and of course reducing also the emissions by the same amount, and that would be around 3,400 tons of CO2 reduced annually. The tilting function on this ship is not because of bridges on the route, but because of cargo handling. So you can see the cargo hatches here. When they open, there is a conveyor belt during loading the iron ore. And then when it's unloading, there are cranes that need to be operating on top of the hatches. So the rotor sails would be in their way if they were upright. So the tilting function is because of cargo operations. I mentioned about wind conditions being very important for determining the benefits of rotor sails, and generally speaking, also any wind propulsion solution requires wind to be efficient. So here we have simulated hundreds of ship operation routes, and the results are here with the blue color showing 500 kilowatts or more of average propulsion power equivalent thrust force, which can be created by one 30-meter high rotor sail for a ship which is sailing 15 knots. So these are parameters which we need to set in our simulator program to achieve the result of average propulsion power savings on long term, and based on the wind statistics that are available for the different regions. And then when we see that the more green ones are areas with lower average wind speeds, meaning that you can expect less fuel saving in such areas and operating routes. And this is a key point when starting a project with a customer to evaluate the benefits and financial performance of such investment. What are the expected savings for that vessel? We've of course studied the market, and we keep a close eye on the shipping and shipbuilding market all the time. But one of the factors encouraging to first of all establish Norsepower, but also to develop further models, invest more into the development, is the huge market potential. We've identified approximately 30,000 ships in the global commercial fleet, which are technically suitable for this type of propulsion system from wind, which means that the total, let's say, available market on average 2 million euro per project would be 60 billion euros. And of course, new buildings will more and more be considering rotor sail technology to be installed together with any other energy efficiency improvements, and eventually the alternative fuels, which will be much more costly than the commonly used heavy fuel oil or other fossil fuels, which we need to eventually get rid of and become carbon neutral and zero carbon operations. The fuel saving potential for one ship is typically between 5 to 25%, depending on how many units can be installed, where the ship is sailing, and so on. But if such installations were made on a very wide scale, we've estimated that global shipping emissions could be reduced by nearly 10%, which is also a huge achievement considering the various ship types and shipping operations going on. The environmental sustainability requirements have become more and more strict also for ships and shipping companies, and they need to find solutions for their both existing ships, so to retrofit old ships to comply with emission reduction target requirements, also making the new buildings suitable for future operation of 25 years, a typical life cycle of a new ship. So whatever the fuels are in the future to be used, whether it's ammonia or methanol or hydrogen or biodiesel, there will be a cost which is likely a multiple of the costs that today is commonly expected. So the savings will be increasing, payback periods will be reduced with technologies that can save fuel. And future concepts include autonomous shipping, so ships without crew on board, fully automatic, obviously high requirements on the digital technologies, connectivity, redundancy, reliability, when the shore-based operations center includes ship operators who are then controlling the ship's navigation and equipment on board. And this kind of a drawing is prepared, including 4 rotor sail units on a ship where there is no bridge, there is no crew on board, which is sailing long distances over oceans with minimum emissions. There are competitors who are developing both similar wind propulsion technologies, but also other types. So clearly wind propulsion is gaining more and more interest, and also then competition starts to be developing. So we are clear market leaders thinking of references and experience of commercially operating installations. But we see also, I have to say, we are glad to see good competitors developing systems that are growing the market and making the marketplace more active with wind propulsion.
And your key winning recipe is, of course, that you have the best available platform for running the environments.
It's a combination of many factors. Of course, technology, including the platform, is of course very important. Certainly the sort of research and product development benefits from digital twin type of projects, but just the practical operation even of the ship and planning proper maintenance and following the trends of different systems to make sure that availability of the rotor sail is high, meaning that it's producing the thrust it should. They require good connectivity and good platforms that are user-friendly and able to support the operations, both local and remote. Yes, there are projects in sort of test phase right now on Norwegian coast, for example, and I think it will take several years before there is sufficient confidence to have wider and longer operating routes. For now, it's more coastal traffic, easier accessibility for such vessels. But for sure, those kind of setups and concepts will develop so that eventually ocean-going traffic without crew will be possible.
If the fuel saving range is now from 5 to 25%, could the savings be more on the longer term? Meaning, can the rotor sails be even longer, or is there a possibility to gain even more capacity out of the existing ones?
Of course, always when measuring the percentages, it's very directly tied with the propulsion power that the ship is using. So if power is reduced, meaning ship is sailing slower, the percentage also will be increasing. But we also see that there are potential for improving the actual efficiency of the units. Perhaps the size of the units will be larger in the future as well, so which means like we have now in just less than 10 years of existence developed the first unit of 18 meters in height up to 35 meters in height today. So doubling the height and almost doubling the diameter of the cylinder. So that kind of trend I see also going forward. So yes, the percentages and also the absolute values of savings will be increasing.
How were the 20s rotor sails controlled before there was the digital controller?
It was more similar to current sailboat control without automatic or autopilot. So you look at the wind conditions, wind direction, wind speed, and then you manage the RPM. Of course, first selecting the direction of spinning, but then you increase the RPM of the unit with increasing wind speed. So it has been earlier quite manual and human control.
Small story about what BaseN is about, why BaseN is on the maritime business, where are we coming from, and what is our task on this digitalization process. That the key point behind this kind of area is that the platform must have certain values where BaseN considers to be the best. We are extremely robust on giving the high availability. When the ships are on the seas, we provide the platform capacity 24 hours a day, 365 days a year, meaning that we are providing the scalability to unlimited amount of ships, and the tens of thousands of crude carriers is something like very good challenge for us to take together with Norsepower. Operating this kind of an environment means that you need to be in position in real time to act on the tasks to manage the object. And the real-time operation is one of the biggest benefits of BaseN. BaseN has been quite a lot involved onto the maritime industries, quite a lot as well driven by the Norsepower's ideas and the strong enthusiasm what they have for the business. Together with Business Finland, we are on the smart shipping projects, on the smart port projects, where we have collected a lot of ideas and a lot of experience how to build the businesses even more intelligent and how to digitalize the maritime industry on the shorter and on the longer period of time.